I would like to welcome Matt Golombek to join us on stage.
Good evening, everyone. Yeah, I'm the Mars landing site guy. And let's see, it's been a while since I was here last, maybe for the last landing site we selected. So where will the Mars 2020 rover go and why? So first of all, what's so cool about this red planet? Why is that gaining so much interest? What's so special about it? We do know from lots of investigations that Mars was probably both warm and wet, and very likely very much like the Earth at about 3.94 billion years ago. What's so special about that? Well, on the Earth, the very first life began at about then, just after the planet had accreted most of its mass. It had gone through terminal bombardment. It had cooled enough. There was liquid on the surface, and life started. And that suggests that life would begin almost anywhere, that the one absolute key ingredient you must have exists. And that key ingredient is water in the liquid phase. So here's our next door neighbor planet, just right next door, the fourth rock from the sun. And it had the same environment at the time when our progenitors sprang to life. So you can ask perhaps one of the most important scientific questions, and you can address it in a scientific manner. Are we alone in the universe? Will life form anywhere that liquid water is stable? Or do you need some one chance in a gazillion that would spark that thing to begin? Was there a second Genesis? Did it happen on Mars? And that's what our Mars program's about. Yeah, it's cool to send rockets to other places. Okay, I'm a space geek, I admit it. but that's the driving question that we want to answer. And this landing site is all about going to a place where the evidence would suggest that the environment was both wet and a place where bugs would like to live, and where they might both have started, and not only did they start there, but you have a chance of sequestering them, of getting them locked up in the rocks so that if you go there and you bring the rocks home, you could see the evidence for it. That's what Mars 2020 is all about. Okay, so hardware. This is a 6-wheel rocker bogie rover. It looks very much like Mars Science Laboratory at Curiosity. Has an arm, and instead of laboratory instruments inside the rover, it will collect samples in little test tubes and seal them, and it will cache them or leave them in a grouping on the surface of Mars for a subsequent mission to go and get and potentially bring home if we like the samples. So how do you get a spacecraft to Mars? Well, you got to stick it on top of a rocket, of course. Here it is from Cape Canaveral. It flies in this kind of configuration with this aeroshell and a cruise stage. It has the same sort of sky crane. Whoever designed that, right? So here it is with the rockets on the back being brought down. The wheels come down and lock into place. And as this thing is lowered, this sky crane keeps the entire system so there's no residual velocity, and it gently puts the rover down on the ground, and you say, this is impossible. Except we did it We did it for the Curiosity rover. Okay, so site selection. I have just one word chart. I know these are horrible. But there's two parts to landing site selection. One is it's got to be interesting, and it's got to be tailored to the science objectives of the mission. And the second is it has to be safe, because it doesn't matter what dancing vision the scientists think they're going to have about what they're going to get when they get there. If it doesn't land safely, you get no science. Bad deal. The site must address the basic science objectives of the mission, and that's an astrobiologically relevant environment. Was it wet? Was it habitable? And could it preserve any biosignatures that might have formed? Could you preserve that in a geologic record. Imagine a stratigraphy of different rocks that could have been inhabitable environments, and you'd know that the rocks at the bottom were older than the rocks on top. And so now you have some known arrangement of these rocks. And it turns out that igneous rocks that form by a primary mantle melt from the mantle, just like our volcanoes do here on Earth, carry a signature of the stuff that they came from. And the mantle is the biggest reservoir in a planet. And so by getting and bringing back those rocks, you can learn about the internal dynamics and how long the planet stayed hot and warm and so on. In order to do site selection, you have to do it as they build the spacecraft. You say, well, why is that? Because no matter what they think they're going to build, there are always things that happen during construction of the spacecraft that change it just a little bit. And if they change it enough, the place that you thought was going to be safe may not be safe when you get to the end. So you have to do site selection during the time that you build it. And for a scientist, I'm a geologist, and by the way, I really appreciate astronomers wanting to hear a geologist. I think that's totally cool. But I have to talk to a lot of engineers. Engineers are not like scientists, okay? Scientists ask, why? Why did this get to be this way? Engineers ask, how? How do you build this thing? But you've got to work together to get this spacecraft to Mars and to land. Okay, so here is Mars. The colors on this map are the topography. Blue's low, red's high. So first off, we can all be geologists for an instant, and I'll give you the 2-minute geologic history of Mars. The southern highlands are all high in elevation, and there's lots and lots of craters, pockmarked with craters. They're side to side. Well, the longer a surface has been there, the more craters it gets. So this surface is really, really old. Okay? However, the northern hemisphere is low, 5 kilometers lower. And what else? Well, there's very few craters. So that surface is young. So first off, something happened very early in Mars's history, and it lowered the northern third of the planet and got rid of all that material somewhere, and left a highlands that was heavily cratered to the south. What do we think that was? Actually, an oblique giant impact, not unlike the kind of impact that probably spun the moon off from the Earth in the very early period. Second geologic event, you'll notice that there's this big red area that's super high, and it has 4 of the largest volcanoes in the solar system. How's that? This is probably the biggest, as big as the state of Texas. It rises 22 kilometers above the datum it started at. That's 10 times higher than Mount Everest, something like that. And then Valles Marineris, which is a rift or a fault that goes radially away from this structure. This is a giant lode on the surface of the planet, and it probably formed very early, and it probably had a lot to do with the early climate on Mars. Okay, so big geology right there. And what's shown in white are the existing safe because the spacecraft survived when they landed. And from start, it's Viking 1, Viking Lander 2, Pathfinder, Spirit, Opportunity, Phoenix, and Curiosity. Look, I did that all from memory. Actually, it turned out I was involved in just about all of those, except for the Viking, so it wasn't too hard to remember them. So what do you see here? So where are all the landers? Lowlands. So why is that? Well, the reason is that somebody knows the answer to that too. More atmosphere, that's right. So the atmosphere on Mars is about 1% the atmosphere of the Earth. And so far, we've used parachutes to slow the spacecraft down. And the more atmosphere you have and the lower in elevation you go, the thicker that atmosphere gets and the more effective your parachute is. So the second thing you notice, they all tend to be near the equator. So why is that?
Warmer.
Right, warmer is right. And more important, if you have a solar-powered spacecraft, blurt it out. Sunlight, right. So you get more insolation near the sun, near the equator. So the problem here is that Mars didn't get the engineering memo about how to cooperate with landers. And you can see here's the equator right there, and everything's too high. You can't land in those spots. There's not enough atmosphere. So where can you land for this spacecraft, Mars 2020? What's shown here is the same topography, slightly color-coded. We got 30 north to 30 south. That's our kind of warm temperature bounds. Anything black is above the elevation at which the parachute can slow the spacecraft well enough, and that leaves these areas that are colored in between, and then there are these white and gray blotches, and those are areas that have extremely low thermal inertia and high albedo. You don't know what that means, but they're composed of dust, fine-grained dust, 1 to 3 microns thick, that is slowly filtered out of the atmosphere and landed on the ground. And in some cases, that dust is meters to tens of meters thick. And we have encountered it at the landing sites that we have gone to, and it won't support anything. It is, your spacecraft would sink right through it. Not only that, if you're trying to get solar power, and you got all this dust around, and you sink into it, and there's dust everywhere, you're not going to get much power. So we basically toss out any of these very dusty regions. So we just got rid of, so plus or minus 30 is about half of the area of the planet. And you can see more half of that area is too high. And another quarter or a third is too dusty. And so now you got to deal with, you got this little slice here and this little slice here and this little slice here, and that's it. That's what you got to work with. Okay, so how do you go to find one of these great places on Mars that has this evidence for potentially biologic activity? Well, I'm not the smartest guy in the world, and nobody else is, but if you had all of those people together and you asked everyone, where would you go on Mars with this spacecraft and this payload, and where would you go to try to find a location that was wet, that could have sequestered any biologic activity that had formed there, and could have had a diversity of rocks that's there for us to go look at now? So we had a workshop, and we invited anybody. Anybody could have come. Completely open workshop, and we asked them, and they proposed 30 sites. Now, in order to determine if the site's going to be safe, we have these orbiters, and we take pictures of these sites. So if we find out about the site, we can then tell the orbiters to take high-resolution images of those sites to say, is it too rocky, is it too slopey, what are the bad things there? So you start taking pictures as soon as you find out what those 30 are. So the first workshop occurred in May 2014, and these 30 sites were suggested by the mostly scientist community, and we started taking pictures of them. And then a year and a half later, we invited everybody back. This is the suite of sites at the second workshop. 8 of them were down-selected from that to look at them in greater detail. Because if you have 30, you can't study them enough to sort of narrow things down. So now we got them down to 8, and we obtained the most amazing suite of images from these sites that exist on Mars. High-resolution images at 25 centimeters per pixel. We could identify a meter-sized object on the surface. We took stereo images so we could create digital elevation models, and we know what the topography was. The resolution was so high we could see any rock bigger than 1.5 meters in diameter.
So you could see the mermaid and the beer can and all those things?
And we could see every previous lander that we ever sent to Mars. And in order to make sure that we measured the rocks right, we measured the shadows that were produced by those rocks. And we took the same pictures of the landers, and we know the size of those because we built them. Right. And we measured those using the shadows, and that's how we calibrated our technique to measure the rocks.
Very cool.
I mean, how silly is that, right? So 8 locations on Mars. And one of them, look at that, right in Valles Marineris. So Valles Marineris is the biggest rift in the solar system. It's 10 kilometers from the top to the bottom. And this particular site is cantilevered halfway down the escarpment, 5 kilometers from the top, 5 kilometers from the bottom, on this little thing sticking out that's big enough that you could just barely get an ellipse in. And the engineers are going, are you sure? There's got to be someplace better than that. Okay, the reason that Laura invited me is that we just had our 3rd workshop 2 or 3 weeks ago. And we went from those 8 sites. We spent 2.5 days talking about each one of those sites in as much detail as we possibly could. And we voted. You know, we had 200 and some odd people at our workshop, and everybody got to vote. And this list is almost like what they voted with the slight minor changes. And the 3 sites outside of, again, the white ones were already there. The 3 sites that were selected are Jezero Crater, Northeast Syrtis, and the Columbia Hills. And you'll notice that the Columbia Hills is right next to where Spirit landed. And that's because Spirit found something that could potentially be of great interest for the next one. So, just rocks. What's making these places so cool? All right, here we go. First out, Jezero Crater. This is a large impact crater. Goes all the way around like this. You can see there's a map channel that comes in here. That's shown here from an enormous catchment basement through the ancient highlands on Mars. This site dates to about 4 billion years in age through nefarious means. This crater filled up with water, and this stream carried water into this lake, and it created one of the most distinguishing geologic features that we know of. And this is a delta. This is a fan where water carrying sediments from that huge catchment at 4 billion years ago on Mars hit an open body of water, and that delta sorts the material that is brought into it by the river. So think about the Mississippi River at New Orleans, where it's carrying all the sediment from the United States out into the Gulf of Mexico, and it sorts it by size. So the bigger stuff is going to fall. It hits a standing body of water. Big stuff falls out first. And it progrades and grows out into this lake in a system of what are called top set, foreset, bottom set beds. And the bottom set beds are out in this nice, quiet water. The little boogers can do the backstroke. There's almost no sediment except clay-sized particles. And clay-sized particles to a geologist are micron size. They're really small, and they've been already water processed to get them to be in that size. And they slowly filter out of the water. Calm water, warm water. It's liquid, right? It's not too cold, not too hot. Liquid water, the clay, and all the little guys that are doing the backstroke. And after they die, they fall on the ground, and the clays entomb them. And the clay is a wonderful sequesterer of any kind of bioorganics that exist. And these are among the most fertile places on Earth. And we can see that same arrangement of top set, foreset, bottom set beds in this delta. So we know that it formed into a standing body of water. It carried sediment from a huge chunk of the highlands that already had clay minerals in them, these iron, magnesium smectites. And it was from a large catchment area, and it came out into this body of water. And if there was things floating around there, it's preserved in the bottom set beds of the delta. Pretty cool, huh? All from a little bit of geology. But let's say you went there and you couldn't be sure that there were actually little bugs in the clay. In addition to that, there's carbonates in outcrops that come out from, this is our ellipse, by the way. It's about 10 by 8 kilometers. That's as good an ellipse as we've ever been able to do. It's nice
and by ellipse, you mean landing ellipse.
Landing ellipse, yes.
So can you say just a word what that is so people know?
So basically the spacecraft, it's, this is going to get complicated, but stay with me. So it's going to come in and it actually has to be targeted to the outer part of the atmosphere at about 10 degrees off of total skip out. So if it comes in any shallower than that, the spacecraft will, like you're skipping a rock. It will actually skip off the atmosphere and keep going. That's not a good thing. If it comes in any steeper, the flight path it takes is not long enough for the aeroshell to slow it down enough such that the parachute would be able to handle the speed it was going to when it came out. It has to hit that. It has to hit it to within, 1/10 of a degree. Okay, so here to Mars, remember it takes 9 months to get there, moving at several kilometers per second. So it's not dawdling, and it's got to hit this spot at just the right spot and angle, such that the flight path it takes as it comes through the atmosphere will carry it to that spot. And we don't know where in that spot it's going to come down, but it has a 99% chance of. And there's always one that's going to be outside. Okay, so within the ellipse is the area that you're most likely to get to with your rover because everything's close. And the closer it is, the faster you get there and the more you can do science with it. So in these areas beneath this cover are carbonates. What's so big about carbonates? On Earth, all carbon cycle is modulated by life. Now, the Earth is lousy with life. Life's everywhere, and it modulates just about any organic functions that exist, and carbon's the number one element for that. So if you strike out there, you got carbonates, and if carbonates were biologically mediated on Mars, there's the great place to go. And the last attractive thing about this site is it has this cover, this gray unit that you can see. And the way we date things on Mars is by counting craters. But we don't know exactly how many craters go to a particular radiometric age. So if we could bring back a sample from a surface that was big enough that we could count the craters on, bring it back and get the age of the sample, we could calibrate that crater curve. Well, wow, that's great. Now we've calibrated our curve, and when we count craters, we actually know the age better than a factor of 2 or 10 or whatever. Okay, so those are the things inside Jezero Crater. And this was the highest ranked or most voted, favorably voted of the sites. And the reasons are just as I said. Okay, number 2 site is northeast Syrtis. And interestingly enough, here's the ellipse here. It's 8 by 12. And even more interesting, I just think this is totally cool, this is Jezero Crater here. So if you got tired of this site, you just go over to Jezero Crater. It might take a little while. It's several hundred kilometers. Okay, this site has basement rocks that are 4 billion years old because it's sitting right next to a giant impact basin that has to be at least that age, called Syrtis. And you can see these mesas with high-standing scarps of what are almost certainly different layers of rocks. And you can see those rocks are exposed and fractured and broken up. So there's rocks sitting at the surface available for our rover to investigate it. And we've got 2 or 3 different rock types in a stratigraphic succession. So I can go there and I can say, oh, what's this? And how do things change when I went a little bit younger? And how did it change when I get a little bit younger? And so on. And the materials that these layers are made up of are clay minerals. Clay minerals form if you take a primary igneous mineral and you chemically erode it with water. On Earth, that happens all the time. That's clay, is dirt, is so on. You break it down, you change the mineral structure, and you add water. And in order to make a clay mineral, you gotta add water. Well, if you've made minerals that had water in them, that could be an aqueous environment, one in which liquid water was there. So here we've got four different distinct environments with very different clay minerals, both iron and magnesium as well as aluminum fiber are clay minerals, and they all have different weathering paths that take slightly different environments. So we have different environments in some of the oldest rocks on Mars. At 4 billion years, Mars had a magnetic field. That magnetic field would have kept all harmful radiation away from it. We think that could have been the most habitable time on Mars. And here's rocks in layers that are chemically processed. In addition, just a little bit further away are these big flat tongues. These are Middle-age Hesperian on Mars basalts, which are primary igneous rocks from the mantle. And these are the key. If we could get a piece of that rock back, we could totally calibrate our crater curve. So that's really liked. And then just underneath it is sulfates that are deposited just prior to that. And those sulfates from our work on Mars is suggesting a very acid environment. So it looks like you went from a neutral pH environment with these clays to an acid environment in the sulfates to our friendly basalts on top. So pretty cool spot. Okay, last one. Oh my goodness, this one has a rock hammer. So this is not from orbit. That's your first key, because we know the size of rock hammer. This is the Columbia Hills. This is where Spirit went as the last part of her mission. And it came across these nodular structures of light-toned materials that were quite hard. We discovered them because one of Spirit's wheels was no longer turning, and we had to drag it across, and it actually broke apart this material. And we looked at it close up, and this material is 91% silica. So the only way we know how to produce that material on Earth is in hot springs. Okay? So don't think of geysers, but think of little hot springs coming out of the ground and going down. And on Earth, hot springs are teeming with life. And they're teeming with a kind of life, we call them chemists. They're autolithotrophs. They live off the chemistry of the water, the minerals in the water. They're not living off the sun. And those are among the oldest and most ancient life forms on Earth by looking at RNA tracking. So if this was on Earth, and here's an analog at the same scale in Chile, up in the Atacama Desert, where you have these same little nodular, again, 91% silica, teeming with life. And the silica comes out, and it sequesters, it entombs the things that are living in the hot water. And so this is a great place to sequester any of those tests from the animals that lived there at that time. In addition, there's a diversity of materials within the Columbia Hills, including volcanic rocks, including that middle-aged basalt. And so this would be a location you could go back. And so the three spots that we've selected are three places where on Earth biologic activity thrives. Deltas in the bottom of a lake, in a hot spring, and I failed to tell you the environment for this one, which is, we think we're probably in groundwater here, just slightly beneath the ground. Some of the minerals here formed under a little bit of pressure, so we think we were just down under the ground. And on Earth, 90% of the biologic activity is actually living down under the ground, and it's these same sort of chemolithotrophic organisms that live off the chemistry. So the three places on Earth where we know that primitive organisms thrive and live, and where you could both have those organisms live and you could potentially sequester the materials that form from them, are the three sites that we have down selected to for 2020. And given the main objectives of the mission of trying to find a place where that material is, and it could have sequestered that material, those are three great places. So where's 2020 going to go? And you'll have to invite me back in about a year and a half, because we will have. So in a year and a half, we will have probably our last workshop. We hope to have all the scientists come back and have arguments for why each one of these sites is the best one that we should go to. And those would be narrowed down and brought to the Associate Administrator for Space Science at NASA for a final selection.